We are back for CSE215. So let's start off with any questions anyone has. We didn't get very far into technical matters on Monday, so... But we will change that today. Alright, let's continue with...
We're going to talk about cardinalities today, maybe?
We may get into cardinality today. If not, then hopefully we'll get into it on Friday. I want to get through enough that we can talk about the homework on Friday. All right, so let's continue set theory. And I'm going to mute everybody's microphone, but if you want to talk, just go ahead and turn your microphone back on. All right, so set theory. So we introduced basic ideas of set theory on Monday. The notion of a set is a collection of things, and we talked about sets being unordered, so there's no inherent ordering to sets, which means that if we write A, comma, B, comma, C, or we write C, comma, B, comma, A, these are the same set, right? It's just a collection of elements with no particular order associated with them. Another thing to be aware of is that a set either contains an element or does not contain the element. And so we don't want to write, for example, something like this. Right, this is not a properly defined set because it's meaningless to list an element twice. It's like saying, who's in the room? Oh, Barbara and Joe and Bob and Barbara, right? There'd be no point to mentioning somebody more than once. And when we list the elements of a set, we're basically saying, from all the things in the universe, tell me which things are contained in the set. Well, A and B and C are contained in the set. And to list B twice, that's a malformed set. So we never want to list the elements of a set where we would list a member more than once. That will be considered an error. All right, we talked about some special sets. So do you remember what a singleton set is?
A single member set?
Yep. So a singleton is a set that contains a single member, such as that. And do you remember what this symbol represents?
Null set.
That's the null set. That's a set containing no elements. So no elements at all, that's the empty set or the null set. One element, any element, but just one, that's a singleton set. And then two or more elements, that's just, a general set. And then we talked about some particular types of sets. So the natural numbers, the integers, the reals, and these are most of where we're going to spend our time in this course. We'll talk about the reals a little bit, but reals are continuous, right? They're fundamentally different from discrete things like integers. And here's one reason. Somebody give me a real number. Any real number you like. 4. Okay, somebody else give me a different real number. 7. Can I find a real number in between these two?
Yes.
Give me an example. 5. Can I find a real number between these two?
4.5.
Yeah, 4.5. I could find a real number between those, maybe 4.1. I can find a real number between those. Any two real numbers I pick, there's always a number in between. In fact, there's a bunch of numbers in between. In fact, there's an infinite number of numbers in between. That doesn't happen with integers. If we were talking about integers, 4 and 7, yeah, we could find a 5 in between, but there's no integer in between those. And that right there is one way to look at the distinction between continuous versus discrete. continuous in some sense. We can keep subdividing, and there's always more space that we can subdivide further. Integers, that doesn't happen. Once we get down to two things that are one integer apart, there's nothing in between. So reals don't come up as often in a discrete structures course as integers or natural numbers or even numbers, but we'll talk about reals once in a while. All right, I think we've got a good quorum of people here, so go ahead and send me an attendance note. Let me know that you're here. So remember, it's your first name, space, last name, dash, and the word here in uppercase characters. And what I want to talk about next is different ways that we can describe sets. So one way that we could describe sets was by saying ... if there was some pattern to the members of a set that was pretty clear. A more precise way was to use this idea of, the set of all x such that some condition is true, such that x is a multiple of 2, such that x is a prime number. But there's other notations. So one notation that we'll see a lot of is what's called interval notation. And interval notation works like this. Suppose we want the set of all x such that x is bigger than or equal to a and x is less than or equal to b. So all the stuff in between a and b, including a and b. We can write this in a shorthand, which is just to say a comma b inside square brackets. And this is usually done for real numbers, but we could do it for integers or natural numbers or prime numbers or anything else. But usually you see this notation for real numbers. And almost the same thing would be this. The set of all x such that x is bigger than a and less than b, but not including a or b. And we use a similar notation for that. We write a comma b, but we put it inside parentheses. And so the parentheses really correspond to the less than and the greater than, and the angle brackets correspond to less than or equal to, greater than or equal to. And this is called a closed interval. And this is called an open interval. And we can do mixtures of these also. We could say the set of all x such that x is bigger than a and x is less than or equal to b. And we would write that with parentheses a comma b and then a square bracket. So sort of generic generalization. So this means bigger than but not including a. This is less than and including b. And so this is sometimes called a half open or a half closed interval. And the difference between these is very, very subtle, right? This is the same thing as this. We've just tossed out a and b. But this is a set, right? If we think of this as being things contained in the real numbers, this is a set with an infinite number of things in it. And so is this. But this looks exactly like that, except we've tossed out a and b. So that may not seem like a huge difference. But there's one really, really fundamental difference between these two sets. So let's look at this set down here, this closed interval. What's the largest number in this set?
1.
Number 1, absolutely. Everybody agree with that? Because 1 is contained in here, and everything in here is less than or equal to 1. So the largest number in here is 1. What about this set? What's the largest number in that set?
That's 0.99 repeated. Infinitely close to 1.
Yeah, so we got a lot of answers here, right? Something infinitely close to 1, which makes sense to us intuitively, but is a little tricky to pin down precisely. Somebody said, you know, a bunch of 9s repeated, which this repeating number is actually exactly equal to 1. There's a little proof we can use to show that. But the weird thing is, you know, any number that you write down is not the largest number. I can write down, you know, 0.999 a billion times, and that's still not the largest number. There's still a number bigger than that, because I could just add one more digit after this. So that's pretty peculiar, right? These two sets look exactly the same, except we've tossed out one number, but they behave fundamentally differently because this set has a biggest number, 1, and this set does not. And that's actually really huge. That is a starting point for a field of mathematics called point set topology. And point set topology is basically abstract calculus. Or put differently, we can derive the calculus that we study in school as one particular example of point set topology. But we can do a much more general calculus, and we can talk about sequences and limits and epsilon delta proofs and so on, using nothing more than just this notion of a closed interval and an open interval. And it's a beautiful branch of mathematics. If you're intrigued by abstract stuff, point set topology is a good starting point. But this is one of these things where moving to the real numbers makes things really kind of like complex, messy, or intriguing depending on your perspective. Mostly we'll stay with integers, and for integers, you know, this is the set consisting of 0, 1. If we looked at the set of all elements in the integers that satisfy this, what is this set equal to? What about a set? Because 2 is a number. But how would you describe the set parentheses 0, comma 1, where x is coming from the integers?
That'd be a null set?
That would be a null set. My microphone's freaking out here. Hold on a second. There we go. We're still good. Yeah, so that's the empty set or the null set, right? Whereas this would be the set containing 2 elements, 0 and 1. So they're very, very different things in the case of looking at integers. All right, so let's look at is this a set?
The set in a set?
It's a set in a set. Is it still a set?
Yes.
Sure thing. We've described sets as just, you know, an unordered collection of objects. Well, if a set is an object, which, you know, it seems like it should be, then this is a collection of one object. It's a singleton set containing Z, right? Z happens to be a set itself instead of a pen or a mouse, but, you know, no big deal. It's still a set. This is another set. So we can have sets that contain sets, not a problem. Except sometimes it will get us into universe-ending paradoxes. But other than that, not a problem. So we're okay with
Like
sets.
a set containing a null set.
So would this be a set?
it is, but at the same time, it's kind of like, is it?
It feels a little weird, right? But it is a perfectly fine set. It's a set containing one element, and that element happens to be the empty set. Here's a set containing two elements. And this is perfectly kosher also. One of the elements is the empty set. The other element is a set containing the empty set. And this whole thing is just a set with two elements. And that's perfectly well behaved. But it starts to feel a little weird to write things like this. But we'll come back to this in a few minutes and see some even weirder, stranger versions of it. Alright, so let's talk about... Yeah, go ahead.
Just to clarify, the set containing the set of the empty set and the empty set is still valid?
That's still valid, yeah. That's a perfectly fine set. Contains two elements. 1, 2. And generally, you know, to know if something is a set, you just have to say, is this a collection of objects? An unordered collection of objects. And yeah, it is. I got two objects. Yeah, those objects are a little weird. They got funny symbols in them and curly brackets, but they're still just members of a set. So yeah, that's perfectly valid. Alright, so what does it mean for two sets to be equal? Basically, it just means they have the same elements. Exactly the same elements. So, if A and B are sets, we can say A equals B, or A is equal to B, or A and B are equal, or, you know, any other version of that we want, but we can write A equals sign B. If and only if A and B have exactly the same elements. So sort of what you would hope for set equality, right? Here's a set with two pens, here's a set with two pens, but they don't have the same members, right? This has a long pen with a red tip, this one does not. They're not the same set.
Could I ask a question?
Sure.
This might be getting a little too far ahead or too far out there. You mentioned earlier that a set containing a duplicate isn't valid, right?
Right, that's not valid.
So my question for you is, in some computer languages, there are things like tuples which allow duplicates.
Mm-hmm.
What would you call...
They're called tuples.
Huh?
They're called tuples. We're going to use that terminology in this course, actually.
In terms of set theory, they're actually called a tuple, right?
They're actually called a tuple or an n-tuple if it's more than two. And they're not sets. They're objects, though, so they could be elements of a set. But here's an example of a three-tuple, right? And I'll write it in parentheses instead of curly brackets to differentiate it from a set. And tuples are ordered, right? There's a first element, a second element, a last element, and so on.
Interesting.
Yeah, so we'll come to these when we talk about some other operations on sets, and when we talk about things like coordinates of a point on a graph, right? It's usually an XY pair. Well, there's an ordering to them, and there's nothing wrong with, you know, having a point whose X and Y coordinates are the same, so that's a perfectly valid tuple. But for a set, we would not want to write 1, 1. So yeah, we'll say more about those in a little bit. All right, so A is equal to B if and only if they have exactly the same elements. And so let me just show you some notation we'll be coming to. Oh, thank you. Wow, got a cappuccino. I didn't see that coming. That is awesome. So saying A equals B means, so we can write this in the shorthand, and we'll talk more about this later, but I'm going to show you a nice way to write this. Alright, so what's going on here? This upside down A followed by an X is a shorthand way of saying for all X. And this IFF is a shorthand way of saying if and only if. And so this sentence says for all X, X is a member of A if and only if X is a member of B. And that's just a long-winded way of saying A and B have exactly the same elements. So we'll spend a few days talking about these upside down A's and then backwards E also. And we'll work with this if and only if quite a bit later when we get into proofs. But in general, we're going to build up this language that we can use to express things that we would write in sentences like this, to be able to write those very precisely and very concisely. So equality is kind of what we would expect, right? Two things have the same elements. So if we keep that notion in mind, and I make a set A which is 1, 2, 3, and I write a set B which is 3, 1, 2, is A equal to B? Yeah, A is equal to B because they contain exactly the same elements, 1, 2, and 3. And this is where the unordered part comes in. Yeah, 3 is listed first here, it's listed last here. Makes no difference. Right? The only thing that matters to a set is which elements of the universe belong to the set. Well, the numbers 1, 2, and 3, the numbers 1, 2, and 3. So yeah, A and B are equal, even though I've chosen to write them in a different order.
So, if B had a duplicate 3, would that mean that that duplicate 3 is just instantly ignored and they would still be equal?
If I wrote something like this, and let me do this in red because this is like evil. Right? If we looked at this, we would say, yeah, this contains 1, 2, 3, this contains 1, 2, 3. I would say they were still equal. But in fact, you know, if this was on a homework assignment, I would probably, you know, put an X here, and I would say not a valid set.
I have a question.
Yeah.
Along the same lines there too. But if you have like 3, 1, 2, 3, a lot of the times that seems like those could represent like different numbers, but that's because the set is actually, like if you're saying test scores and two people got 3s, the actual set is made up of those individual, like the abstract symbol of those people's names, and then they're just assigned a different value or the same value.
So this is an interesting area. So if I was just recording test scores, right, that would not be a set. That would be, I don't know, a collection maybe, but it would be probably an ordered collection because, you know, two people might have gotten the same score. Now, if I took all the names of students, right, that would probably be a set because they're probably unique, but sometimes not. I've had classes with 2 students with the same name, but technically they would not be a set if there was an element that would appear more than once.
Okay.
And if
C wouldn't be sets either, because if you had 2 consecutive numbers that were 4 stored in memory, they would just be integers 4 and 4.
Yep. So arrays are definitely not sets. And in Java, there's different kinds of collections, right? And you can have a set which will only have an element once or no times, or you can have other kinds of collections where you could have things appear more than once.
What if
if the second 3 was in its own set? Like, what it was 3, 1, 2 in its own set, and then the 3 in a set within a greater set? I don't know if this, like, is that a set?
So this would be a valid set. And this set would contain 4 objects, a 3, a 1, a 2, and a set containing 3. That's totally
It would
fine.
not be equal to A, right?
But that's definitely not equal to A, correct? Because this contains this object, a set containing 3, and that's not contained in here. And so this is all good setup for the notion of subsets. So A is a subset of another set B, and we write that with a sideways U with a line underneath it. So this means A is a subset of B. So this means if X is contained in A, then X is contained in B. So equality means these sets have exactly the same members. Saying A is a subset of B means everything that's in A is also in B. But there could be things in B that aren't in A. So in this example, we would say A is a subset of this, right? Because A contains a 1, that's in here, contains a 2, that's in here, contains a 3, that's in here. So if this was our set, let me make it C, right? We would say A is a subset of C.
So by saying that, does that basically just mean A or C contains everything that A has, but there's also more stuff in C basically?
But there could be more stuff that C has, yes. But it contains everything that A has.
Okay.
But if we use this as a definition, if X is in A, then X is in B, we find the following unusual characteristic. A is a subset of A. Because if X is in here, it's also in there. Now this is kind of silly, but it's a true statement. And subset works kind of the way it does, you know, in common usage. You know, I like Star Wars, but there's a subset of them that I would love to see, you know, again. So it's a collection of some members of the set. But in fact, you know, a set is a subset of itself. What's even a little more peculiar, the empty set is actually a subset of A. And this one gets a little stranger to think about. But look at our definition. If X is in A, then X is in B. Okay, so to say that this is a subset of A means if X is in the empty set, then it's also in A. Well, there's no X's in the empty set because it's empty. So this is actually considered to be a true statement. It's true in this sort of vacuous sense because there are no members of the empty set, so there's nothing in the empty set that's not in A.
So we're not specifically talking about like a member set inside of the set. We're talking about a portion of a set.
So we're describing one set being a subset of another, but the meaning of that is that the meaning of that is that the elements of this first set are contained in the second set. So the subset notion is about two sets, but the definition relates to the elements in those sets, if that makes sense.
Is there ever a situation in which the null set isn't a subset of another set, or is that pretty much always?
Actually, the null set is always a subset of every set, which means also, you know what I'm going to write. The subset is the empty set is a subset of the empty set. And now we're just down to nonsense, basically. But it's a true statement, so.
Power sets are coming up, I assume.
Absolutely. So these two things are always true, which means every set always has at least two subsets, right? Except the empty set. It's always got the empty set and it's got itself. And so we have a different notation and a different concept, which is a proper subset. So A is a proper subset of B if it's a subset of B but it's not equal to B. And a proper subset we write with a similar notation, where we put a little slash through that line. And it means A is contained inside B, but it's not exactly equal to B.
So long as A is a proper subset of A.
Correct. Yeah, so the empty set's a proper subset of every set except for the empty set itself. Yes, yay for the unideal segfault universe. Good stuff.
So why does the null set exist then? Like, is it like the same reason we have a zero? And like what's its purpose if it's like everything? You know what I mean?
That's probably a question we could spend multiple lifetimes analyzing. The not as deep, quick answer is it's useful in talking about, for example, how many integers, what's the set of integers bigger than 2 and less than 3? We could say there is no such set, but there is a set. It's a set containing nothing. It lets us talk about nothingness without really treating it as a special case. It's still a set. It's just a set that happens to have nothing in it. What's the set of integers that are divisible by 5 and less than 3? Well, there are none, right? Positive integers. But we can describe it as a set. It's just the empty set. But if you really want to spend some time, go off and look at some Sartre. There's a beautiful work called Being and Nothingness that might be the longer answer to that question. It's a lifelong goal of mine to get further through that text than I have. But it's I think a really interesting question to be able to write down something that represents in some sense nothing. It's a really powerful concept. It's kind of like the concept of zero that not all cultures have developed.
I've read that Western culture didn't really have a reason to use zero until like the 1500s. That's when we came up with it.
Yeah, and apparently I think I read that the Egyptians did have a notion of zero, but the Romans didn't. And that's kind of interesting. And yeah, we didn't need complex numbers till we understood, equations and algebraic manipulation. But the degree to which math or science, or math in particular, mimics or explains or extends or stands in contrast to reality, I think is always an interesting question, and definitely one we could spend a lot of time on, but I will try to control myself. Alright, so some examples. So 2, 4, 6, that's a subset of the set of integers. And in fact, it's actually a proper subset of the set of integers. The set of integers is a subset of the set of reals. Because any integer that you can think of, 5, negative 12, 11, 0, those are also real numbers. But it's definitely a proper subset because, for example, 2.5 is contained in this set, but not contained in that set. So they're not the same set.
So a proper subset has the little plus under the sideways U, right?
Yeah, it's actually, that's sort of the subset symbol saying this is contained in there. This is a shorthand for equal. So kind of like less than or equal to, right? But with a curly less than sign. Less than or equal to, that's what a subset means. If we put a slash through that horizontal bar, then we're just saying something like less than. So it's contained inside that, but not equal to. So I think that's the derivation of those symbols. If we have something that's not a subset, though, right? There's some numbers in common. There's a 4 here and a here, but the 2 is not contained in this set at all. So that's not a subset. And so we write that as, the subset symbol with a slash through it. And we do this a lot. We put slashes through things to negate them. So epsilon is a membership. Epsilon with a slash through it means not a member, and so on.
So the whole set would have to be represented for it to be a subset.
Yes, for this to be a subset of that, we would need all of these things to be in that set. So there'd have to be a 4, but also a 2 and a 6. And then there could be other stuff also, that's okay. It could be bigger than this set, but it would have to have all of these elements.
And it would be improper to switch their orientation, right? You couldn't say, like, if they were, the first set was all the same and switched around. Like, couldn't say that B is a subset of A, right? It's just not, it's directional.
It's directional, so Z is a subset of R, but R is not a subset of Z. Because 2.5 is in here, but 2.5 is not in the set of integers. So usually it's directional. But this actually gives us our first sort of theorem. So what does it mean if A is a subset of B and B is a subset of A? Suppose we can switch it around. Suppose both of those things are true. What's going on there?
And they're the same.
And then they're the same. Yep. So here's a bit of a theorem. A is equal to B if and only if A is a subset of B and B is a subset of A. And the if and only if means, right, if this is true, then that's true. And if that is true, then this is true. They're equivalent conditions. So that's a bit of a theorem, and we could prove this pretty easily, but the proof is almost too simple to write down formally right now. But remember what this statement means. It means if X is an element of A, then it's an element of B. And this says if X is an element of B, then it's an element of A. And this says X is an element of A if and only if it's also an element of B. And if you work with the wording a little bit, you'll see that these two statements together are exactly the same as saying, every element of A is an element of B and every element of B is an element of A. So this proof would be really just a restatement of the definitions of what this defines, and what this defines, and then observing that they're basically saying the same thing. So we won't worry about proving that at this stage. Alright, so how many people here are familiar with Venn diagrams? Seen a few.
Yeah, I've heard of it, can't remember exactly what it was.
So here's an example. A Venn diagram is basically a picture or a graphical way of describing sets and relationships among sets. So for example, this could be the whole universe, and I'll write a universe with a script U. So let's say the universe equals the set of all foods. So that's all we're talking about for our sets. Everything that we describe as being in a set is going to be a food of some type. And so I could make a set C. So this is separate from this. Let's C equal the set of all cookies. And this might look something like this. So I'll draw, a closed shape, something roughly like a circle, to represent this set C. That's the set of cookies. And I could have, V equals the set of vegetables. And yeah, in some parallel universe, there are cookies that are the same as vegetables, but not in my universe. So here's a set of vegetables, okay, and here's a set of cookies. And they don't have anything in common. There's no element of the set of cookies that's also an element of the set of vegetables, and vice versa. And you can see that in this picture because there's no overlap. Alright, so let me make another set. L equals set of foods containing chocolate. Well, the set L I would draw like this. It's got some overlap with the set C. Why? Because chocolate chip cookies exist in our universe, right? And so there are some elements of the set of cookies that are also elements of the set of foods containing chocolate. And so there's an overlap area here, which I can shade in like this. So these are chocolate cookies. And if you did chocolate covered broccoli, right, then you might have some overlap with the set of chocolate and the set of vegetables. And maybe D equals the set of desserts. And if it was true that every cookie and every food containing chocolate is a dessert, then I would draw my set D to contain both of these sets. So this would be the set D.
Not to be technical, but you do have carrot cake, so couldn't these
And rhubarb pie, like, come on, man.
Yeah, so we should have some overlap there. I guess if we say V is a set of foods containing vegetables, then we got some overlap. Yeah, and I'll definitely hang with carrot cake and rhubarb pie. So we can look at a pictorial notion of this idea of equality and subsets, right? So I mean, V and C are definitely not the same set, right? In fact, they may not have any members in common. L is not a subset of C, right? Because there's, chocolate bars that are not a cookie. And C is not a subset of L because there are snickerdoodles which don't have chocolate, right? But C is a subset of D, and L is a subset of D, right? And C and L have some overlap, and that overlap is also a subset of D. And if we took the collection of everything that's a cookie or a chocolate, if we took the combination of these two sets, it's still a subset of D. And all of these things are a subset of U, the universe, which in this case is a set of all foods. So Venn diagrams are just kind of a graphical way that we can look at different representation of sets and their relationship. We cannot prove things using Venn diagrams, usually. But we can use Venn diagrams to help us see what's going on, and that may help us construct a formal proof. For example, if A is a subset of B and B is a subset of A, if we try to draw that, we're going to realize the only way we can make that work is if A and B are exactly the same set. If there's anything sticking out from one set that's not in the other, then one of these subsets will be false. And so that may lead us to understand how we could formalize a proof showing that this theorem is true. So we can use this as a different way of looking at problems involving sets, but we don't prove things using Venn diagrams because, for example, how do I know what the shape of this is? How do I know how big the overlap is with the set of desserts, and so on and so forth?
I have a question. How do you, is there a helpful symbol to show like, B is in no way connected with C?
Yes. We will get to that. We'll get to that today. The question would be intersection. And we can define what the intersection of two sets is. And if the intersection is the empty set, then they have nothing in common. But we'll tighten that up in a few minutes. All right, let me talk about I feel like I skipped something. Okay, let's talk about power sets. Very, very basic notation. Working with it can get tricky, but the concept is pretty straightforward. We know what subsets are, right? And we know that most sets have, at least one, but usually two subsets, the empty set in itself. But for example, suppose I take the set consisting of the number 1, the letter A, and a smiley face. Alright, so that's a set containing 3 elements. And I know that if I want to list the subsets, the empty set is a subset, and S is also a subset. But there are other subsets as well. So somebody name another subset. Or tell me what the elements of another subset would be.
The set containing the smiley face?
Set containing the smiley face. That's a singleton set. And that's definitely a subset of S. Any others?
The set containing 1A.
Set containing 1 and A. That's another good subset. Anyone else?
Cameron in the chat said the subset containing 1 and smiley face.
Set containing 1 and smiley face. That's a good subset. Any others? This is like calling bingo at the end.
A and smiley face.
Set containing A and a smiley face. That's a good subset.
Set containing A?
Set containing A. That's a good subset.
How about a set containing all of them? 1A and a smiley face.
Set containing 1A and a smiley face. So I abbreviated that with S. But yeah, that's definitely a good subset. And someone said 2 curly brackets, that's the empty set, and a few people said in chat, and just now the set containing 1. Any other subsets? So if we were playing...
Power sets are just the set of all subsets of a set.
Yep. So if you write down all of the subsets, and you put those inside another set, that's called the power set. And we would write that as, I write it as a script P, of S. So this is the power set of S. And it's the set containing all subsets of S in this case. So the power set itself is another set, and the elements of the power set are each a set themselves. And the power set is the collection of all subsets. So if we do a smaller example, let's just take the power set of the set containing two elements, 1 and 2. And it's going to be the empty set, the entire set, or one of two singleton sets. And I believe that's all the subsets.
You can also like take the power sets of all real numbers and get a huge number.
Oh yeah, definitely. So the bigger this set is, the bigger the power set's going to be. In fact, when we had 2 elements in our set, the power set had 4. When we had 3 elements in our set, the power set had 8 elements. And if I start off with something with just, one element in it, like the letter X, the possible subsets of this singleton set are either the empty set or the set itself. So a single element only has 2 elements in the power set. So if the size of the set is 1, the size of the power set is 2. If the size of the set is 2, the power set has 4 elements. If the size of the set was 3, the power set had 8 elements. Want to take a guess if the size of the set is n elements, how big the power set will be? Yeah, I heard that from a few people. 2 to the n. Right, 2, 4, 8 looks like a reasonable pattern. And in fact, this turns out to be the correct formula. So if my set has no elements, how big do I expect the power set to be?
1.
1, right? That's 2 to the 0. Well, let's try that. What's the power set of the empty set? There's only one subset of the empty set. That's the empty set. But this set that I just wrote contains one element. That one element is the empty set. So this formula holds even for a set with 0 elements. And we will prove this formula eventually several times this quarter. This is going to come up not only in set theory, it's going to come up in proofs, it's going to come up in doing combinations and permutations and statistics. It's going to come up when we represent numbers in binary. It's going to come up when we look at truth tables. This is going to pop up again and again and again. And we're going to see a lot of different demonstrations and examples of this notion of a number of subsets of a set. But this gets weird when your set has an infinite number of things in it, because 2 to the infinity is not a number, right? All of these things that I'm writing down, these are integers. Infinity is not an integer. It's something different. And 2 to the infinity is something very different. So we'll talk about that more another time. Let's do one more thing with power sets. So the power set of the empty set is a singleton set containing the empty set. What if I take the power set of the empty set?
When you get the empty set and then the set containing the empty set?
That's what you would get. So I'm taking the power set of a singleton. Don't worry about what phi is. Make it a smiley face if you like. This is just a set containing one element. And the subsets of that are the empty set and the set itself. I can take the power set of the power set of the power set of the empty set. And I'm just looking for subsets of this collection of two objects. So I know it's going to include the empty set. It's going to include this set itself. And it's going to include a pair of singletons. A singleton containing the first element and a singleton containing the second element. There you go. This will start driving you crazy pretty quickly. We're not going to go on beyond 3. Well, we could. But hey, guess what? 1 element, 2 elements, 4 elements. So if I threw another P in front of here, I'm going to end up with a lot of elements. The power set of something containing 4 elements has 16 elements in it. And it's going to be a big, horrifying mess of twisty-turny brackets that all look the same. And so this is a lot we can do with an empty set, right? Something that's presumably nothing. We can start getting into some interesting areas from there. All right, send me an attendance ping. Take about a 5-minute break, and we'll come back and we'll start looking at other operations on sets. So we'll come back in about 5 minutes. let's talk about set operations. So a lot of what we do in math and logic is we create new things from old things. That's sort of a pathway to discovery sometimes. So a lot of what we do with set theory is we create new sets from old sets. When we get into propositional calculus, we'll talk about creating new propositions from old propositions. This will be kind of a recurring methodology for discovery. So throughout all of this, let's just say let A, B, and C be sets. So I don't have to keep writing let A and B be a set. So A, B, and C are just going to represent sets. So one operation we can do is called the union. And so a union looks like this. So it's a U for union. And this is the union of A and B. And it's the set of all elements X such that X is in A or X is in B. So we're putting the sets together basically.
So it's basically we just took A and B and mashed them together.
Just mash them together, yep. So if I take the set 1, 2, and I take a set 3, 4, and I take their union, I get 1, 2, 3, 4. But suppose I take the set 1, 2, and I take the union with the set 2, 3. What do you think I end up with?
1, 2, and 3?
1, 2, and 3, thank you. Right, I'm not going to write down 2 twice. Because, right, a set is just saying which elements are members of the set. 1, 2, and 3. Yeah, 2 kind of got counted in there twice somehow, but we don't get to record that when we write down the set. So even though 2 is here and 2 is here, the union is just the 3 elements, 1, 2, and 3. And if we take that to an extreme, 1, 2, and we union it with 1, 2, what do we end up with? Just 1, 2. And in fact, for any set, if we take its union with itself, we're just going to get that set back. So union is one operation we can do on sets. Another set operation we can do is intersections. And we write an intersection with an upside down U. And this is a set of all elements X such that X is contained in A and X is contained in B. So it's the stuff that's in common between the two sets. So if I intersect 1, 2, and 2, 3, what will I end up with?
2.
Yep, just a singleton set containing 2. And if I take 1, 2, and I intersect with 3, 4, what do I end up with?
Null set?
Null set, so there's that empty set coming back into play. And so someone asked a while ago, how can you represent two sets that have nothing in common? Well, that's one way to do it. Just state that their intersection is the empty set. And in this case, where two sets have nothing in common, we can say that these sets are disjoint.
So the intersection of those two sets would be null set, yeah.
So the intersection would be the null set, so we say these are disjoint. And on a Venn diagram, we can represent these characteristics. So here's our universe. And maybe here's one set A, and here's another set B, and another set C. So the space where they overlap, that would be the intersection. And if we look at the collection of everything that's in either A or B or both, that's the union. And if we look at the overlap between, say, A and C, there is none, right? And so the intersection of A with C would be the empty set. Empty sets are hard to draw in Venn diagrams because they're nothing. It's hard to draw nothing. All right, the complement spelled wrong.
The operation just before complement intersection?
Yeah, so we did an intersection,
Okay.
which was the things that are in common to both, compared to the union, which is the things that are in either set. So the complement of A equals the set of all X which are not contained in A. It's the stuff outside of A.
So what's the limit on that? Would be like, I mean, if A equals just 1, right? It's a single set of 1. Would that mean the complement is literally every other number?
So we have to be careful here. We have to know what the universe is. So I should probably write the set of all X contained in the universe. But we're assuming when we just talk about the complement that we know what the universe is.
Okay.
And so for the case of a Venn diagram, for example, if this is the set C, the complement would be everything that's outside of C. And we write the complement as the set with a bar on top of it. So the complement of A would be A with a bar on top.
So it's kind of like in binary or when you're doing that kind of stuff. So if the complement of 0 would be 1 and vice versa.
Yeah, if you only had two things, 0 and 1, then yes.
Okay.
And sometimes you see this written as A with a little C on top. That also means complement. Sometimes that's easier to typeset than putting a bar on top of a letter. But there's a more general notion of complements, which is the complement of A in some other set S. And this is the set of all things in that set S which are not contained in A. So we can talk about the complement of A in the entire universe, or we can talk about the complement of A in some other set. And so for example, if this is our set S and this is our set A, then what would the complement of A in S be? It would be all of this stuff. It's the stuff that's in S but not in A. And so this kind of looks like start with S and take away the things that are in A. And so this is sometimes looked at as subtraction. S take away A.
Would your line above where you have the X in the element of S such that X An element of A, should that be not an element of A?
Yes, thank you. Yeah, so the x and s, such that x is not an A. So we can write this as s minus A, or a more common notation is s with a backslash followed by A. But the essence is, you know, start with s and then throw away anything that's in A. And so the complement of A in the universe is the set of anything in the universe that's also not in A. This is really just the universe with A subtracted from it, or the universe backslash A. So the complement, A with a bar on top or with a little c, is a particular case of this more general notion of the complement of one set in another. In this case, it's the complement of A in the universe of all sets, of all elements. Alright, so let's work with these concepts in a little more detail. So for example, if I take A union B, I'm going to get exactly the same thing as B union A. And if you think about our definition of union, right, it's the set of all things that are in X or that are in A or B. This is the set of all things that are in A or in B. This is the set of all things that are in B or in A. They're pretty obviously the same set, right? And similarly, if we do an intersection, the order doesn't matter there either. This is the set of things that are in A and B. This is a set of things that are in B and A. Right? It's going to be the same set in the end. So we say that the union and the intersection operation are commutative. Or this is the commutivity property. Okay, what happens if I take A and I union it with the empty set? What do you think I end up with?
Will it just be A?
Just ends up being with A. Because this is the set of things that are in A or in the empty set. Well, there's nothing in the empty set, so this is exactly the set of things in A. So it's just A.
So both unions and intersections are both commutative, right?
They're both commutative, correct.
Okay.
What if I intersect A with the empty set?
Results in the null set, yeah?
Yep, that's going to be the null set, because this says I want all the elements that are in A and also in the empty set. Well, there is no such element, because there's no elements in the empty set, so this intersection is just the empty set. Okay, what if I take A and I union it with the entire universe of all objects that I'm interested in? What am I going to end up with?
Just U.
That's going to be the universe of all objects. Because this is anything that's in A or in the entire universe. Well, that's the entire universe. What if I intersect with the universe?
Also just A.
That's just A. Tell me everything that's in A and also in the universe. Well, that's just everything that's in A. What about A union the complement of A?
It'd be the universe.
That's the universe. This is everything that's in A or not in A. Well, that's everything. What about A intersect the universe?
So we did that.
What about A intersect the complement of A?
Null set.
That's the null set. Everything that's in A and not in A, well, there's no such element. So that's the empty set. This will also turn out to be true, and this will turn out to be true. These are distributive laws. Does any of this look familiar to anybody?
Boolean algebra.
It looks like Boolean algebra. Guess what? It is Boolean algebra. If we replace union with or, and we replace intersection with and we replace the empty set with 0 and the universe with 1, these are our laws from Engineering 250. So here's another thing that's true. Anybody recognize this?
De Morgan's.
That's De Morgan's theorem. It works for sets also. So all the stuff that we learned in 250, that big table that we saw in CSE120, Engineering 120, that talks about set identities, right? These all carry over to set theory. Sorry, they talk about Boolean identities in 120. Yeah, this is set theory. It's the same thing, right? Now, set theory is a much older discipline than Boolean algebra. Boolean algebra, 1850s, George Boole, right? But it's exactly the same mathematics. And this is not a coincidence. There are a lot of things that we develop and we work with and we use that are all the same as something else. Right? This is KVL, KCL from 120. KVL and KCL are not two things, they're one thing from two different perspectives. Well, set theory and Boolean algebra, same thing from different perspectives. And we're going to see this pop up a lot in this course and, you know, in other courses too. But this means all the stuff that we learned about in Boolean algebra we can apply in working with sets. And that's going to be pretty powerful. And we can continue this, right? The empty set, if you take the complement of that, you get the universal set. If you take the complement of the universal set, you get the empty set. If you take the complement of a set A, you get A. And so on and so forth. But we won't be making any traffic lights in this course, so that's the good news. All right, let's see. We got about 5 minutes left. Let me start talking about membership tables. Suppose we want to prove that this is true for sets. Well, we can use the definition of union and complement and intersection, and we can write, you know, lots of things with fancy words, and we could probably prove this eventually. But there's a really easy way to prove this using something called a membership table. And here's the idea. We're going to consider any element in the universe X. Just pick some element X. Okay, I don't know what it is. You're thinking of an X, I'm thinking of an X. They're probably different. But here's what we can say. Whatever element X you're thinking of, there's two possibilities. It might be a member of A, or it might not be a member of A. And I'm going to represent both of those possibilities with a 1 or a 0. If the element X you're thinking of is not a member of A, I'm going to write down a 0. If it is a member of A, I'm going to write down a 1. And now I'm going to consider the set B. And if the element X you picked was not a member of A and also not a member of B, I'm going to write down a 0 for A and a 0 for B. If it was not a member of A, but it does belong to the set B, I'm going to write a 1 for B and a 0 for A. If it's a member of A and not B, I'll write a 1 for A, a 0 for B. And if your element happens to belong to both A and B, I'll write a 1 for A and a 1 for B. And I think you'll agree that one of these four conditions will always be true no matter what element you think of. No matter what set A and B are, whatever number you think of, whatever element, whatever smiley face or object or pen or mouse or whatever, right? Either it's not a member of A and it's not a member of B, or it's a member of both, or a member of just B, or a member of just A. So these four conditions describe the state of any element's membership in A and B. And for different elements, right, different situations will apply. But what I'm trying to do is enumerate all the possibilities for any element that you think of. And now I'm going to say, what can we say about that element's membership in A union B? Well, if your element's not contained in A and it's not contained in B, is it contained in the union?
No.
No.
Right? By definition, to be in the union, it has to be in either A or B. Well, if it's not in A and it's not in B, it can't be in the union. But suppose it's in B and not A, will it be in the union?
No. Yes.
Yeah, if it's in B, it'll definitely be in the union, because the union is the things in A or B. And if it's in just A and not B, that'll be enough to be in the union. And if it's in both A and B, is it in the union?
Yes.
Absolutely. In fact, we have to erase one of them from our memory so we don't accidentally list it twice.
So union is basically an inclusive OR.
So union looks just like an inclusive OR. Hey, there's our union symbol, there's our OR symbol. Coincidence? No. Alright, what about complements? If something is not in this set, is it in the complement?
Yeah.
Right? The complement is all the things that aren't in this set. So if an element is in this set, it's not in the complement. So that's the membership for your element in the complement of A union B. And hey, guess what? Complements look just like complements in Boolean logic. Zeros become ones, one becomes 0. And so if something is not a member of A, it is a member of the complement. If it is a member of A, it's not a member of the complement. And I can do the same for B bar. And now let's look at intersection. So if something is in this set and that set, it's definitely in the intersection, right? Because the intersection is a set of things that are in here and also in here. Well, if my element started off not being in A or B, then I know it's in A bar and it's also in B bar, so it's in the intersection. But if it's not in B bar, is it in the intersection of something with B bar?
No.
Right? And if it's not in A bar, that'll kick it out of the intersection. And if it's not in either of these sets, there's no way it can be in the intersection. And this is just a logical AND of these two columns. And so intersection works the same as a logical AND. And now we do what we did in 120. We make the following observation. Hey, this column looks exactly like that column. What does that mean? It means for any element that we pick, if that element belongs to A union B bar, it also belongs to A bar intersect B bar. And if it does not belong to A union B bar, it does not belong to A bar intersect B bar. So we've just shown with this membership table that an object belongs to this set if and only if it also belongs to that set. Well, that's our definition of equality of sets. Ergo, we can make the following statement: this set is equal to that set. That's a proof of De Morgan's theorem for sets. But hey, you know what? This is just an engineering 250 proof using a truth table. It's exactly the same thing. When we prove De Morgan's theorem in 250, this is exactly what we write, except this is a V and this is a caret. But everything else we've done, exactly the same. Alright, that's a good place to leave things off now. So send me one final parting attendance ping, and we will continue this on Friday. We'll talk about the first homework assignment on Friday, which will basically be playing around with sets and set operations, memberships, things like that. So it'll be a chance to just sort of work on some of this stuff on your own. Alright, have a good afternoon. It's been raining a bit, but it looks pretty nice out there. And I will see you tomorrow or next time in 215.
Thank you, sir.
Your day?
Thanks.
Could I ask you a question from the 224 class?
Only if it takes like 5 seconds, because I have an appointment in 68 seconds.
That's alright, I'll show up tomorrow for the class.
Okay. Alright.
Off hour.
Sounds good. See you then.
Have a good one.
Alright.